Wakey, wakey, explorer! The dawn of day 3 is upon us, and as much as I'd love to let you slumber in peace, we have an ocean's depth of work to tackle. Do you recall our incessantly blinking LED from yesterday? Well, today we're going to show those painstaking glimmers of light who's boss. Enter the dip switch. This nifty little piece of hardware will allow us to control the blinking at our will. It's going to be the relentless leash of our overzealous LED. Of course, to make this happen, we're going to need more than just some physical wiring. This is where things get cerebral. We're going to be introducing some conditional logic into our code, a touch of if this, then that. All right then, a flashy switch and some smart code are on our horizon. Rest assured, by the end of the day, we'll have our blinking light under control. So, whenever you're ready, Explorer. Though, regardless of your readiness, we must begin. Right. Let's not dilly-dally. Our main character today is the dip switch. This fellow might look simple with its array of tiny switches, but oh, can it wield a great deal of power. You see, DIP stands for Dual Inline Package. It's essentially a manual electric switch that's packaged with others in a group. The switches are all housed in a single box and can be toggled on or off independently. You may think of this like a tiny panel of light switches, each controlling a separate room in a miniature dollhouse. Each position of the individual switches in a dip switch represents a binary condition, which simply means either on or off, high or low, 1 or 0, yes or no. The magic lies in the fact that you can manipulate these switches to control different parts of a circuit. In our case, the part of the circuit we're so keen to dominate is that perpetually blinking LED. By the end of today, that LED will be blinking only when we want it to. The power of control is within our grasp, Explorer, so let's grab it. Allow me to introduce some vital elements. The ground, or GND, and voltage, or VCC. They are, you could say, the lifeblood and nervous system of our electronics. Ground, my friend, is the common point of reference for all voltage sources in a circuit. It's our zero voltage reference line, the foundation on which all other voltages are built. Without it, our circuits would be aimlessly wandering in the wild, uncertain about where the bottom of the voltage range lies. It also provides a path for our electric currents to return to their source after their exciting journey through our circuits. Now, let's talk about VCC. This little gem is the primary source of power to our hero board. It stands for Voltage at the Common Collector. In plain language, it's the positive supply voltage. If GND is the foundation, then VCC is the engine that powers the machine, the fuel that keeps the circuits alive and kicking. You see, in a system like ours, having a common ground, such as GND, and a common power supply, such as VCC, is essential. It allows different components of the system to communicate effectively, each understanding what the zero and full points of voltage are. This way, when signals or power move between different parts of the system, they all understand the language of voltage in the same way. It's like our own language, really. If we didn't have common reference points and shared meanings, we'd be unable to communicate and collaborate. And we know that wouldn't end well, would it, Explorer? Moving on. The extra resistor. A keen observer, aren't you, Explorer? You see, the extra resistor we're talking about is what we call a pull-down resistor. Its job is to make sure our circuit behaves properly when the switch is off. Without it, our switch being in the off position could cause our circuit to get all wonky. Imagine it like a crowd of electricity not knowing where to go and causing a ruckus. We certainly don't need more chaos around here. What the pull-down resistor does is finish the circuit and acts like a form of crowd control. When the switch is off, it guides the confused electricity safely away, down to the ground. This way, our circuit stays composed and organized, just the way we like it. Remember, Explorer, every brick in a building plays a vital role in keeping it standing. Similarly, every small component in a system is crucial to its overall functionality and success. Now, let's return to our task at hand. Now that we've solved the mystery of the pull-down resistor, let's turn our attention to something absolutely fundamental in electronics, the concept of inputs and outputs. Think of our system as a living organism. It needs to inhale data inputs to process and exhale data outputs as a result. An input is essentially a message received by our hero board. It could be from a sensor, a button, or in our case today, a dip switch. These inputs tell the board what's happening out in the world. In this instance, whether our dip switch is on or off, or high or low. On the other hand, outputs are signals sent out by the hero board. Outputs could be triggered by code conditions or other sensor readings, like the position of a switch. Examples include spinning a motor, sounding a buzzer, or making an LED blink or stay solid. Today, our dip switch is the input, telling the board whether the switch is on or high, or off or low. The LED is the output, responding to this input by either blinking or staying off. Great! We're done playing with our hardware for now, Explorer. Don't look so relieved. The fun is far from over. You already know what's next. Programming our newly created circuit. So, grab another gulp of that precious oxygen and brace yourself for a thrilling journey into the intricacies of code. Let's power through, Explorer. The sooner we do this, the sooner you can get some lights on in here and stop groping around in the dark. Well, Explorer, you've stumbled upon a fairly straightforward piece of code here. Let's dissect it together, shall we? First, we're defining two variables, one for our LED and one for our dip switch. These numbers are currently configured to represent the pin numbers on the hero board where your switch and LED are connected. In the setup function, we're telling the hero board how to treat the two pins we defined earlier. The pin mode parenthesis function is used for this. We will make the LED an output, meaning we want to send out a signal from this pin to control the LED. We will make the dip switch an input, meaning we expect to receive a signal from the switch to this pin. Next, we move to the loop function, the heart of our hero code that, as you know, runs continuously and repeatedly. Inside loop, we have a new kind of statement, an if statement. I can see from the look on your face that cadet training never taught you about conditional logic. Humans are such ineffectual creatures. All right, time for a bit of theory. Fear not, Explorer, it won't bite. Conditional logic involves creating rules within your code based on certain conditions, much like deciding to wear a spacesuit before you step out into the vacuum of space. Simple. Would you agree? The main tools for this in C++ language are if, else if, and else statements. Let's break them down. If. This is the primary decision-making tool in your code. If a certain condition is true, then some code will run. For example, if oxygen levels are less than critical, we initiate emergency procedures. This only happens if the condition is true. If the oxygen levels are measured to be fine, the code within the if statement is ignored. Else if. This comes into play when you have more than one condition to check. It's like saying, if the first condition isn't true and doesn't apply, we'll evaluate the next one. It's important to note that an else if always follows an if or another else if. Else. This is the last resort. If none of the previous if or else if conditions are true, then the code in the else block will run. It's like saying, if nothing else works out, let's do this. Here's a quick example. You'll notice that we always indent everything inside sets of curly brackets. This simply allows for better readability of the code. In this code, the ship checks the oxygen level and responds appropriately based on the conditions we've set. I hope this brings some light into the murky depths of conditional logic for you. Let's see if we can apply this to our switch situation next. When the switch is on, digital write is executed, turning the LED on, or high, as you could say. This sends current to the LED. If the switch is off, the else block is executed instead. Here, digital write is run, which grounds the LED's circuit, turning it off. So, this code is continuously checking the state of your switch and turning the LED on or off accordingly. Quite easy, don't you think? Now, let's try this out on your end, Explorer. Oh, my. I'll give you credit. You have a keen eye. Good on you for noticing that. You've stumbled upon one of the classic conundrums of programming, Explorer, the tale of two equals. They might look similar, but they have different roles in the programming universe. Let's clear up the confusion, shall we? In programming, a single equals sign is known as the assignment operator. It's used when you want to assign a value to a variable. Think of it as the word is in English. For example, int my variable equals 10 semicolon is like saying my variable is 10. Now, a double equals sign is a completely different beast. This is the equality operator, and it's used to compare two values to see if they're equal. If they are, the comparison returns true. If they're not, it returns false. This is used a lot in conditional statements like if statements. Here's an example. So remember, one equals sign is for assignment and double equals sign is for comparison. It's crucial not to mix these up. Trust me, it'll save you a lot of headache in the future. Ah, it seems to be that time where we cut to the instructional material I was able to gather, cached on the computer. Like the exceptional AI that I am, I've also added this to your mission resources for future reference.
Hello everybody and welcome back to day 3 of fixing your spaceship. Now yesterday we were able to successfully get your LED to blink on and off every second. Now unfortunately that's not very useful, and while it is saving a little bit of battery, it's pretty much useless because 1, you don't have any control of turning it on and off when you need it, and 2, it's not saving as much battery as it could. So when you go to bed and it's just blinking for no reason, obviously that's quite a waste of battery, especially in a critical time where you guys are stuck at the bottom of the ocean. So we're going to fix that today. We're going to take yesterday's circuit and we're going to build upon it. So we're going to take what we had then and we're going to add an input, a dip switch, and to allow us to turn it on when we need it and off when we don't. So to start, I'm going to take what we had from yesterday's circuit and just redo exactly what we had back then. First, you can grab your breadboard, and like we talked about yesterday, I like to start by taking a pin here from ground and going just straight into ground, and you can also change the wire color just for good consistency. I'm going to use black for this just because that's what I think is generally typically used for ground. And then for voltage or the 5-volt signal, I'm going to run a wire from the 5-volt and I'm going to go directly into, you guessed it, the red line right here. And I'm going to change this wire color to red so that we know that this is the 5-volt line and then this black one is the ground line. That way it's just easy to read. Next, I'm going to take the LED and I'm going to plug it in right here. And don't forget, we need our resistor. And we're going to set this to 220 ohms. And then we can wire directly from here straight into the 12-volt. And I'm going to change this wire color here since it's not grounded. I'm going to change it to something like orange. And then here, I'm going to take the cathode line and wire it directly into ground and change that to black so that everything is nice and pretty to look at. Next, we're going to get into the new input device that we'll be using today. This is known as the dip switch. Now, Astrid already went over quite a bit on this in the video previously, but this is what we'll be using. It's going to be the 4 input for our purposes. So our goal for today is we want to make it so that when we flip this switch into the on position in the simulation, it's going to turn this LED on. And when we flip it into the off position, it turns it off. Instead of yesterday's useless blinking on and off, while it's good for understanding how coding works, it's not really good in practical application. So to do this, we're going to need to use a pin on the board as an input. We're going to need to have some pin that's designated to read as an input to say, hey, when the value on this pin changes, calculate or turn it on or turn it off. And so the input pin that we're going to be using for today, it could be any one of these pins realistically, but for our purposes, we're going to use pin 2. So what we can do is we can actually go straight from pin 2 directly into, boop, right there, into this line here where it goes into 1. And I'm going to change this color just so that it's nice and easy to read to yellow. Next, we're going to take on this side of the pin, of the switch, and we're going to take a line here and go directly to the 5-volt line. Now you might be wondering, why am I doing this? Well, the way the logic is going to work eventually in the code is we want to be able to see, for example, when we actually are having a 5-volt switch coming to our side, then it's going to read a 5-volt signal here, meaning we want to then turn on the LED. If we don't read that signal, meaning that the flip is switched in the other direction, blocking that, it's going to read nothing, and it's going to tell us to turn the LED off. So essentially what the switch is doing is it's basically allowing that flow of the signal through, or it's not allowing it through. So depending on whether it's able to read that something is being flown through here to this side here and into pin 2 or not, is going to give us the logical reasoning in our code for turning on or off our LED. Now there's one issue with this, and that's that we don't have a reference for where ground is. So our circuit is not technically 100% complete. We need to have a very defined value for what is ground. And so we can fix this by adding in a pull down resistor into our circuit. Wow, I wish I could type today. So yes, a pull down resistor is quite literally a resistor. It's a resistor, and in our case, we're going to be using a value of 10K. And what we're going to do is we're going to, 10K ohms. And this quite literally just sets it to ground. So this is so we give our circuit a reference value of where ground is. What is ground value? So that anything above that, 5 volts up, is considered high. And with this, we should have a completed circuit. Obviously, it's not going to work yet. We do need to add some code logic to actually make that work. So if I did hit start simulation, it would just take the code we had here, which is obviously blinking our LED on and off, and that's not what we want it to do yet. So let's hop into the code and let's go in and explain how we're going to fix that. So as you know, yesterday we introduced cabin lights is going to be pin 12. That can stay the exact same. However, we also need the cabin lights switch, the thing that's going to be controlling it. This is going to be our input device that we just added. That's this switch right here. So we can actually add that up here. Define cabin underscore lights underscore switch pin. And we're going to set this to pin 2. This is the input device that's reading right here on this line here. So if we go add a little comment here, switch for light. Next, we need to go into setup. Obviously, we just added an input device, so we need to define in setup all of our inputs and outputs that we have for our entire program. Yesterday, we already added the LED cabin lights, so that's already an output. But now we have a new device that's the input, so we can actually just write pin mode, cabin lights, switch, cabin light switch pin, and we're going to set this as an input. And don't forget the semicolon. Now, technically, as we mentioned the other day, you could just put 2 here and it would still work. And going out anywhere else in the code, wherever this is, you could put 2 because that's what define does. It quite literally says wherever this is, just swap it with the value here. But obviously, I'm going to use good coding practices and just in good readability practices, and I'm going to continue to use the define that we put up above. Next, we're going to hop down to our loop, but you'll notice that our loop right now is just telling our cabin lights to blink on and off and on and off. We don't want that to happen. We want to have a little bit of a conditional logic here. This is where we're going to introduce a new statement. Astra did mention this a little bit, but we're going to go into it in a little bit more depth here. We only want the lights to turn on if what we read on the switch pin is high. So if this is not being blocked, basically it's in the on position, and this 5-volt signal can then run through all the way back here to our pin 2, and pin 2 is then reading the 5-volt signal. Only if that's the case, basically meaning it's in the on position, do we want to actually turn on the switch, on the LED. If it's not, well, we want to keep it off, right? So we need a bit of conditional logic to make that happen. Well, if we can use the new function digital read, which is for inputs. So digital write is for outputs. It's sending, writing a signal to an output pin. Digital read is reading from an input pin. It's reading the signal that it's being sent on the pin. So digital read is used for inputs. Digital write is used for outputs. But essentially they act pretty similar. We can say digital read, cabin, lights, switch, pin, double equals to high. And I'm going to quickly delete all this. So what this is saying is if the value that the pin 2 is reading is 5 volts, meaning that this signal is successfully going through, basically meaning that it is turned on, that the switch is turned on. If the switch is turned on, then what do we want to do? We want to digital, not read, write to our LED, cabin, lights, pin. Again, writing to our LED, cabin lights pin is 12, it's going straight to our LED. High. Basically, we want to turn it on when the switch is on. The other condition would be, otherwise, what happens when it's not on? Else, we can write digital, write, cabin, lights, pin, we can set it to low. This is essentially the equivalent of saying, the shorthanded version anyway, since we only know there's going to be since we know for a fact there will only be 2 cases. It's either going to be on or it's going to be off. There's no other case that it really could be, luckily, because this is a pretty simple situation with the switch. It's quite literally on or off. We can shorthand instead of saying if digital read cabin light switch pin equals high, have this up here, and then have else if digital write cabin light switch pin double equals low, we can rewrite it. We can just switch it to else, because again, there's only 2 situations it could be. You could write, here's an alternative to this. If you erase this, I'm just going to comment this out and just show you guys an alternative. Else if, and we just take this and say that it's going to be, let me just quickly fix that. Else if it's low, then we digital write to low. But some shorthanded version is just say, we can go else, which is exactly what we had here. Digital write cabin lights pin to low. Now, if we want to simulate this, hopefully it should all be working. Hopefully I didn't forget any syntax anywhere. Oh, and would you look at that? I guess I did. Expected. Is that right? There we go. Syntax error. Happens to everybody. Now, if I hit the simulation here, you'll notice that the LED is currently off. And what happens when I flip this little switch here? It turns on and it turns off. It turns on, it turns off. So right now, when it's in the off position, the 5-volt signal that's being sent from right here is blocked. It's not going through right now. The switch is not letting that signal go through, and 2 is not reading anything. It's reading 0. It's reading nothing right now. And because of that, we have in the statement here, it's not reading high, so it must be reading low. And in that case, we're going to turn the LED off. And then when I flip the switch, I allow the signal to then pass through here and complete the circuit, going to 2. In the loop, it recognizes this. It says, hey, cabin light switch pin is obviously, we're reading a high signal on it. So what do we want to do? We want to set this to high. And there you go. Now you have a working cabin lights for at least the cabin portion of your ship. In the next couple of days, we'll have the logic to do the rest of your ship lights for the breaker room, bathroom, whatever. All those will be fixed in a future day tomorrow. But with that, that should end this section of the wiring and code. I wish you best of luck, Cadet, and safe travels.